Hi, this is Professor Fernandez, and in this video we are going to go through Module 2 of Lesson 11. So we're still talking about double and triple integrals over general regions. In this module we're going to talk about triple integrals over those general regions. So the first thing that I will say is that we are going to talk about triple integrals over a general solid region E in R3. And remember that when we talked about triple integrals in the previous lesson over rectangular regions, very specific types of solid regions, we eventually reduced the calculation to a double integral after we integrated once. So let's start in this new generalized context with the perhaps simplest case when the region E is bounded above and below by two surfaces, U1 and U2. So let me just draw out what this looks like. So here is my prototypical region that we are going to start generalizing into. It used to be the rectangular, the box from the previous lesson, lesson 10, but now we're going to generalize to a slightly more interesting region. So this is a region that has a lower boundary, some upper boundary, and this upper boundary is z equals u2 of xy. This lower boundary has equation z equals u1 of xy. And both of them have the projection onto the xy plane of some region D. And so, the solid is this part, everything in between these two equations for z. So that's what we're going to call a type 1 space region in R3. So let's see what this definition says. So let E1 be a solid region in R3 that can be expressed as the set of points in space such that x and y are in D. Okay, so every point in here is an x comma y point. And when I look at the z value corresponding to those points, to that point xy, it has to be somewhere between u1 of xy and u2 of xy. So if I look up here, whatever this z value is, it is somewhere in my solid between this point, which is the u1 of xy lower boundary for my solid, and this point up here, which is the u2 of xy upper boundary for my solid. So you can see here that we're generalizing the type 1 plane regions that we talked about in the previous video just to this three-dimensional context. And we think, therefore, of D as the projection of E1 onto the xy plane. And U1 and U2 are functions. We're going to assume they're continuous so that the solid E is nice. So that's what we're talking about for a type 1 region. Basically, if I wanted to illustrate this in the real world, take the boxes, in a manner similar to what we did in the previous modules video. Take the boxes we've been talking about, rotate them so that they look like this, and then put them somewhere over the xy, into the xyz axes. Their projections would be the rectangles that we're used to working with, and now mess around with the top and the bottom of the boxes and make them a little curvier. Curvier in the same sense that when you project them onto the xy plane, you get the same D here. And that's the picture that we're going for on the left-hand side here. So that is one way that we're generalizing away from these rectanguloids, these boxes in space, to these regions over here. And then pretty much everything that happened in the previous lesson, in the previous module, will happen once again. We have yet another version. I didn't call it Fubini this time, but this is certainly another version of Fubini. So suppose f is continuous over a type 1 space region, E1 and R3. Then the triple integral of f is the double integral over D of the integral from u1 to u2 of f, dz. So kind of what you would think, again, going back to this idea that we introduced in the previous module, if I draw now this line segment, the lowest z value is u1 of x1, the highest z value is u2 of x1, That explains my bounds down here for z. And then once I integrate out the z here, then I am back to a double integral over the region D, right? So again, I assume that these two functions projected, the entire solid projected onto the xy plane. Great. So what do I do now? Well, I'm going to show you that things can get more complicated, but we are going to very quickly try to simplify our lives. In many cases, the projection of a type 1 space region onto the xy plane, what we are calling D in this new definition, it turns out to be a type 1 plane region. What do I mean? So I'm going to draw you a picture here. Remember that type 1 plane regions go from A to B in X, and then they have like a lower boundary and an upper boundary. So this lower curve is y equals g1 of x. This upper curve is y equals g2 of x. That's what we called a type 1 plane region in the previous module's video. You can imagine now that I might have a solid whose base projects down to this, and up here the base also projects down to this, right? So I've kind of tried my best here to picture such a strange solid, and there we go. So this would be a region in space, a type 1 space region, that would have the characteristics of x being between A and B, because the projection onto the xy plane here, over here, you can see is between A and B. Check. Y is between G1 and G2. Yep, that's what's happening over here. And then Z is between U1 and U2. That's this bottom curve here, and this bottom surface and this top surface. In other words, it is possible, as I'm illustrating here, that a type 1 space region generates or projects down to a type 1 plane region. However, it is also possible that the same type 1 space region projects down to a type 2 plane region. So what would that look like? So here is a picture. Very similar. Remember first that a type 2 plane region goes from C to D in Y, and then has a left boundary and has a right boundary. And the left boundary is x equals h1 of y, and the right boundary is x equals h2 of y, and then everything in between is our type 2 plane region. So imagine now just drawing a solid that projects down to this type of region. So here is my attempt at illustrating that. What would this solid do? Well, it's still got its upper boundary of U2. It's still got its lower boundary of U1. So the Z range here does not change. But now what changes is exactly what we're talking about here, the D domain, right? The stuff that's happening in the xy plane. In other words, this little bit for the type 1 plane region is a type 1 plane region. This little bit here is a type 2 plane region. However, both of these are type 1 space regions because at this point, that refers to this last bit here. They are both type 1 space regions because Z, the new kid on the block for this module, is bounded between a lower surface and a upper surface. You can therefore imagine that things, as I hinted to earlier, could get much more complicated. We could, for example, have a type 2 space region with a type 1 plane region or a type 2 plane region. Or you could have a type 3 space region with a type 1 or a type 2. So lots and lots of possibilities. I mentioned, let me scroll down, after all of this, which we'll do an example in a minute, I mentioned that down here. And I very quickly say, if you're interested, here are some resources where you could go and investigate and learn about that. However, for my purposes, things have gotten complex enough that I will only ask you about the type 1 space regions. Their planar regions might be type 1 or type 2, but I'm not going to get into type 2 space regions, type 3 space regions. These are effectively like, instead of having U1 and U2 be bounding surfaces that are below and above. You could have a U1 surface that is bounding from the left and from the right. You could have a U1 surface that is bounding from the front and from the back. Right? So these give rise to the type 2 and type 3 space regions. But again, we don't need to go there. This is enough for us to deal with in this video. So once again, we meet the Fubini theorem generalization to this context. I did put Fubini in here this time. And the generalization is what you would expect at this point. If f is continuous on a type 1 space region, whose projection to the xy plane is a type 1 plane region? Well, we can at this point work through this. Type 1 space means that z is bounded between a lower surface and an upper surface. Type 1 plane means that x goes from a to b, and then y goes from lower curve to upper curve. Great. So that's exactly what you would expect and what turns out to be true for evaluating this integral. If, however, you're still dealing with a type 1 space region, but the xy plane projection of that space region is a type 2 plane region, then what you would expect. The z bounds don't change because that's what makes it a type 1 space region. However, the x and y bounds do. Now y goes from c to d, and x goes from h1 to h2 of y. Great. So with that out of the way, let's look at an example. So we are going to evaluate this triple integral over where the E is the solid tetrahedron bounded by 0, 0, 0, and this plane. So this one is a little bit easier to draw than we have than the one that we did in the previous modules video. So I'm going to draw this excuse me, by the usual approach. If I set z equals 0, I get the line 1 minus x. Looks like that. Where this is 0, 1, 0. And this over here is 1, 0, 0. If I set y equals 0, I get z equals 1 minus x. So that is a downward sloping line here. And the point above there, z equals 1 minus x, so 0, 0, 1. And if I set x equals 0, I solve for z, I get 1 minus y. So I would get this line over here. So my tetrahedron is then, or this plane is this part, just the top of it. And I'm being asked in this example to think of E as the solid bounded by x equals 0, y equals 0, z equals 0. These are all planes, and this other plane. So my tetrahedron includes this face, and then everything back here stops over here. So it's the solid that is made up by everything under this plane and above the xy plane and bounded by the xz plane, bounded by the yz plane, bounded by the xy plane. Okay, so that's E. And I want to find the volume of that, or sorry, I want to find the triple integral of the function z of that. Okay, so how are we going to set this up? Well, notice that we are integrating z. I can easily solve for z over here to get 1 minus x minus y. So this is exactly the situation that we were just talking about. I have an upper surface for z. You know, my tetrahedron stops at this plane, 1 plus x plus y plus z equals 1. My tetrahedron starts at this other plane, z equals 0. So those are my two bounding surfaces. So when I set up this integral over here, I've effectively set up the z bounds already. I'm integrating z from 0 to 1 minus x minus y. Great. And then I am left doing a double integral over the planar region that this z plane, you know, this one, projects down to. So let's draw that. What is the planar region that it projects down to? Well, you know, it's kind of embedded in here. It's this 1 minus x that we had gotten, y equals 1 minus x, going from y equals 1 all the way down to y equals 0 at x equals 1. And so we can use all this information and again think, should we do this integral as a type 1 plane region or a type 2 plane region? Again, in this case, if you have noticed by now, usually defaults to type 1 plane regions. We're more used to doing that. Certainly that was the case in Calculus 1. So therefore we have a lot more practice with that. So if I do type 1, then I'm thinking of x going from x equals 0 to x equals 1. And I draw a representative line, x equals constant. And then I see that x goes from y equals 0 to y equals 1 minus x. So those are my bounds for x. For y. So I'm going to put in here dy going from y equals 0 to y equals 1 minus x. So I'm just working now on the d version, the d portion of this integral. And then my x bounds I got here from x equals 0 to 1. That's my dx. Great. And then I'm just going to try to see if the iPad will let me kind of copy just this part. Let's see. Oh, I think it's going to work. Great. And it didn't quite fit, but you get the idea. So I have now set up my triple integral. As usual, I will do a little bit of this and then encourage you to calculate the rest of it as practice. I'm integrating z with respect to z, so that turns out really nicely to be z squared over 2 from 0 to 1 minus x minus y. And that leaves me with this expression of, I don't have to really put the 0 in there. I'm going to subtract 0 squared. So really I just have 1 minus x minus y squared over 2. Great. Add dy dz. Great. So at this point we are back to the same types of double integrals that we have been solving in the previous lesson. There are all sorts of things you could do here. You could square this out and multiply things and it'll get kind of ugly. Or you could try to integrate this by using the fact that for the y integral here, right, we are just integrating with respect to y. So x is a constant. So it's like if I was integrating 2 minus y squared, let's pick a different number, 3 minus y squared over 2. Same choices. You could multiply this out, or you could do a U-substitution. You could say, oh, if u is 3 minus y, du is minus dy, and then do the integral that way. We have the same choice here. A very, very quick way to do the U-substitution is to think of this integrand in the same way as 1 minus x minus y squared over 2 in the same U-substitution way. If I integrate this, you might think 1 minus y minus x cubed over 3, and maybe some other negative sign somewhere. So, we don't know that yet, so we can take this expression and differentiate it with respect to y, a partial derivative. We would bring down the 3, the 2, and then times the derivative of the inside with respect to y, which would give us a negative 1. Okay, so we don't have that here, so we put it in. So this is, if you haven't seen this before, a quicker way to do a U-substitution without going through all of the details of let u be this, and then du is minus dy, and then running through the substitution. So long story short, what I have just shown you is a very quick way to get to the next intermediate step, which is that this integrates to 1 minus x minus y cubed over 3 with a negative sign out front. And then we would substitute in y equals 0 to 1 minus x. And then we are left later to do that portion of the integral. Okay, so I have done enough here that I've shown you all of the new stuff, which is the space region E here, projecting down to a planar region where we decided this would be fairly easy to do as a type 1 plane region. we set that up this way. And then I showed you a little technique here that you can do a quick U-Substitution, even in this context where you're dealing with two variables. So you can continue this integration here and verify later that you get 1 over 24. We were calculating a volume. Oops, sorry, I lied. We were calculating a triple integral of z. So if this z were a 1, remember we talked in the previous lesson that then we would be calculating the volume of a region. So we have done enough in this example to illustrate the new stuff. So I'm going to go on to the second example. I'm going to remind you here of what I said earlier, that there are things like type 2 space regions, type 3 space regions. I won't focus on them in this course, very similar to what you do with type 1 space regions. But in case you are interested, you can click on this webpage to read more about them. The last thing I do want to emphasize and make sure that we can do, and we've done this in a few places already, is continue practicing the skill of changing the order of integration. Remember when we talked about this way back, when we were just starting to talk about double integrals over rectangular regions, we learned that you could integrate in either order. First with respect to x, then with respect to y. As things have gotten more complex, the changing of the order of integration has gotten more complex. So now we are at triple integrals, and I just wanted to give you an example of how to do that. Notice that in this example it says change the order of integration below to first with respect to x, then with respect to z, then with respect to y. We're not told the integrand. So the whole point of this example is just to help you practice that skill of changing the order of integration. It really does not matter what the integrand is. It really is just about knowing how to set up the integration region in a different way from what is provided. Okay, that being said, it does pay to think a little bit about what information you're initially given. So in this initial information that we're given, what are we told? Notice that first we integrate with respect to z. Z goes from 0 to y. So if I were to draw out, in terms of y, a function of z, I go from 0 to y. So I'm just going to draw z equals y. Z equals y. Okay, and then I integrate y from 0 to x squared. So I'm going to draw this y as a function of x, and I go from 0 to x squared. So already I'm getting information about what the region of integration looks like. And then x goes from 0 to 1. And that kind of closes the loop. So I go back here and I say, oh, x goes from 0 to 1. And that means that y goes from 0 to 1. So I go back up here and y goes from 0 to 1. So z goes from 0 to 1. So again, by thinking very carefully about the order in which things are happening, I now have a pretty good sense of what the region of integration looks like. So now I can start to reverse it, or at least change it in the way that they asked me to. The second thing I want to point out here is that notice that these limits are not numbers. So we're not dealing with a rectanguloid here. We are dealing with some region that has some curviness to it. But at the very end of the day, z integrates to something as a function of y. And then y integrates to something as a function of x. And then x is going from 0 to 1. So at the end of the day, we get a number, is the thing that I'm really trying to point out here. So this is what I'm about to say is a way to check your work. Whatever we do when we change the order of integration, we should also get a number. If somehow, the last integral we do, let's say we're supposed to do y. If somehow the last integral we do is y and y goes from 0 to z, then we've done something wrong, because that's going to yield a function of z. Right? So with that being said, right, now we look at all of the clues that we have assembled here, and we notice that y is the last variable that they want us to integrate with. Notice in these regions that y always goes from 0 to 1. So actually that takes care of the last part, the last integral that we are going to do. So that leaves, first we want it with respect to x, and then we want it with respect to z. Okay. So if I have integrated y last from 0 to 1, I can now do this in whatever order I'd like, but let's look at x. Where would I start? Well, if I want to integrate with respect to x and then with respect to z, right, then I need some way to express the x and y and z bounds in terms of y. So I'm going to go back here again to my picture and look at x and z in terms of y. So that then I can integrate x and z, be left with y's, and then integrate y from 0 to 1 and get the number that I knew from the beginning should result. Okay, so how do I think of x and z in terms of y? Well, so here is a relation between x and y. So that is x equals square root of y. Great. And then here is a relation between z and y. So that is z equals y. So these are the two things that tie for me x and z to y. So now we go back to our f of xy as our first integral. So where does x go from? Well, if I look at this picture and I'm thinking about x, that means that I'm drawing a y equals constant line. And x is going from this boundary, the left boundary, to the right boundary. So I'm going from here, which is square root of y, to here, which is 1. So x goes from square root of y to 1. Great, so that integrates out the x, and I've now used this picture. So now I'm going to go up to this picture. So now I'm integrating with respect to z, and I am going to try to do z in terms of y. So I have a very similar thing going on here. So I want to figure out what is the lowest that z is in terms of y, what is the highest that z is in terms of y. So I'm drawing here a vertical, y equals constant. Remember, y here is the independent variable. And y goes from z equals 0 to z equals y. Z goes from 0 to z equals y. So those are my bounds for z. Z goes from 0 to z equals y is the upper bound. And I have arrived then at my first guess. It's always good to guess and then check at what this rewritten triple integral is. We've used this figure here, and then our last integral here would be with respect to y, and we'd go from 0 to 1. And then if we go back to each one of these pictures, if I go to this top one and y goes from 0 to 1, well, then I would be drawing those line segments, and I would get the entire triangle. Great. And then if I go back to this picture down here and y goes from 0 to 1, then y here is going from 0 to 1. So that's y equals 0. There we go, going to 1. So I get the entire region again. So this is therefore the integral that we are left with after we do this revision with the order of integration. So again, we don't know what capital F, or lowercase f here is, the integrand. Doesn't matter, because we just wanted to change this region of integration to a different region of integration. You might ask why, how does this help, why would we ever want to do this? You've seen now us making various choices as we approach a double or a triple integral. Sometimes we choose a type 1, for example, plane region, representation of the double integral portion of it. Sometimes you choose a type 2 plane region. When you actually write out those differences, that equates to different bounds for the integral. So put another way, if someone gave you a double integral with bounds already, kind of like what's happening here, and for whatever reason you already have your integrand and you look at it and you say, this is too difficult to evaluate this way, I'm going to find an easier way, then you have to be able to change the order of integration, and that generally changes your integration bounds in order for you to actually carry out this other way of integrating. So this is, again, a skill to practice, and in the practice problems and throughout many other practice problems in previous lessons, you've been kind of tinkering with this idea. So that is it for this lesson. I refer you back to this web page over here in case you're interested in the type 2 and type 3 space regions. And then I also want to encourage you, as I did with the previous video, to go back and fill in some of these extra steps here, again, to make sure you're practicing your integration skills. And I will see you in the next lesson.